check. All right, advanced placement chemistry. This is a day 75 assignment dealing with VSEPR and hybridization. And let's go ahead and take a look. These problems, you do not have to do all of these. The ones I want you to do, I actually have copied on the assignment. This was from last year, but I just wanted to keep track of the problems that I did. So it says, do only the problems on this sheet. All right, it's not all of these. So only do the ones down below that. Okay, so if you want to do the rest of them, you're welcome to. The more you do, the better you'll get, and I can give you answers on those if you want to do that. Okay, so let's get going on this. So what is a hybrid orbital? All right, so a hybrid orbital is a mix of S and P, X, Py, Pz suborbitals, possibly d orbitals, that produces energy levels between S and P to form chemical bonds. So you only form hybrid orbitals when you're forming a chemical bond. An atom by itself does not form hybrid orbitals. It must be involved in a chemical bond to do that. And so the energy level is somewhere between the S and P. It's so that you have equal, different bonds in that molecule will have the same energy levels that are somewhere between this lower energy level and these which are higher. Okay, so draw the 2s and 2p, 2y, and 2z orbitals. So the 2s, again, you can get this straight out of the notes. So the 1s would be right there. And then the 2s is, it covers that, and it also covers outside, but it has something called a node. And that is right in here. It's kind of an area where the electron doesn't want to be. So the electron wants to be here, or it wants to be out here in the 2s. We'll write that. That's the 2s. It doesn't tend to want to be in here. Why that is goes way beyond the scope of what you need to know. That's really advanced atomic theory, why it would skip over this area. But that's too. It's basically, it's a spherical orbiter. So you can just write that. It's a sphere. It's basically a ball, okay? All right, 2py/pz. So this is, and you can orient them however you want. So we'll draw different books do it different ways. So we'll say this is the x. I like the x to be the one this way in between atoms when I draw it. The y we'll say is this one, and the z is the one coming out of the page towards you, okay? So we'll say that the px is this one. So I call it the potato orbital because they don't really look like potatoes, but you can kind of say that just so you use the letter P for potato. And this is the px. Okay, so both of these are px, not just one of them. They're both the same orbital. They're px. This can hold up to 2 electrons. It's not necessarily true that one of the electron, these different parts of it are called lobes. It's not true that one electron will always be in this one and one in that one. That would seem logical, and that might be. But they're just somewhere in these 2 lobes, okay, for the px, the 2 electrons for the px. All right. Then you can have the py. And that's going to look exactly the same. Again, these are all in the notes. And this is the up and down one. This is horizontal. This is vertical. And finally, you can have the pz. And you kind of have to use your imagination, the perspective, that that's coming out of the page toward you. This one. And that this one, we'll draw it as a dashed line, is going back into the page away from you. Okay? So this is away and toward you. All right, and that is the pz orbital. So in all, this can hold 2 electrons, this can hold 2 electrons, this can hold 2 electrons. So that would be a total of 6 electrons in the p orbital. And if you think of the second row p orbital, that goes from boron over to neon. And so that would hold those 6 electrons between, boron, carbon, nitrogen, oxygen, fluorine, and neon. Okay, draw a 2sp hybrid orbital, and the remaining p orbitals draw in relationship to 2s, 2px. Okay. So I drew these as a diagram, but in this one what I'm going to do is draw them as energy levels and Aufbau energy levels. So this is what they physically look like if you were to actually be able to see them. But on this one what I'm going to do is draw it like this, and you could have done this up here, but I'm going to draw this as 2s, and up here, okay, there's 2px, 2py, 2pz. So the 2sp is going to take these two right here. One s, the s, there's only one of them, and one of the p orbitals, we'll say it's the px. And it's going to form a hybrid orbital that's going to be halfway between these two. So it's like you mix a cup of apple juice and a cup of orange juice. You're going to have half a cup, it's half of what you get is going to be apple juice and half's going to be orange juice. So we're going to call this 2sp. And this happens when you have a central atom has bonds in two different places. That would be an example, would be like carbon dioxide. It bonds to an oxygen on one side, it bonds to an oxygen on the other side. That's a 2sp. Now what about these two? They stay unhybridized, so they stay at the same energy level, okay, and they stay up there. So if carbon dioxide bonds, it bonds, one of these is on the oxygen on the right side. Let's just draw it real quick. Okay, so one of these is bonding over here, that's an sp orbital. And one of them is bonding over here, that's an sp orbital. The two just means it's in the second energy level. And that's what that would look like. Now that's one of these. Okay, but what about this second bond? Double and triple bonds are formed from unhybridized p orbitals. So these two are unhybridized. They didn't join into this mixture between like these two did. So the double bond would be this one right here. That would be causing that double bond right here. And if you have 2sp, you could also even have another bond. That would be a triple bond. Now carbon dioxide doesn't have that simply because it doesn't have enough electrons. You have to have enough electrons to be able to form the additional bond there, and that would be a triple bond. So only 2sp orbitals can have both double and triple bonds. All right, in this case carbon dioxide just has a double bond, so that's an arrow right there. Okay, all right, so that's how you would draw. That's how this, when it bonds with oxygen, is going to form this. Again, this only happens when it's bonding. It doesn't just spontaneously, the carbon doesn't just spontaneously turn into this. It has to be bonding with something, and in this case it's oxygen. Okay, let's keep going. So draw the 2sp2. So again, I'm going to draw just a standard 2s and the 3p orbitals. Okay, and when we have 2sp2, what that means is an s, a p, and a p. And again, the 2 is just referring to the second orbital. It could have been the third orbital, it could have been the fourth, but we're dealing with just the second. So you're going to end up with 3 bonds. All right, so it's going to be these right here are going to blend together. And they're going to be, since there's 2 p's and only 1 s, they're going to be closer to this level than to this level. So I'm going to draw them right about here. And that last one that doesn't hybridize, the pz, is going to be in its same location. It's at the same level. All right. So that's what that would look like. And okay, so what you can look at is these 3 form a bond. So an example of that would be right here, boron trifluoride. There it goes. It forms kind of a triangular trigonal planar shape. Looks like that. Now, this can form a double bond. It doesn't in the case of BF3. BF3 is on your sheet. I just showed it to you, but it's like that. Looks like that. But you notice ozone is also, it's also an sp. Everything that has 3 electron domains is an sp2. So that would include ozone, and you notice ozone does have a double bond. So again, an unhybridized p orbital can form a double bond. Now 2sp2 can only form double bonds. It can't form a triple bond because it would need another sp orbital, and it doesn't have it. It only has 1. So this can only form a double bond. Unlike up here where you had 2 unhybridized sp orbitals, two unhybridized p orbitals. Let me correct that. Two unhybridized p orbitals, and that could form a double bond and then a triple bond, even though it only formed a double bond with carbon dioxide. Okay, there's that. Now we're going to move on. Now we're going to do sp3. This would be typical of methane. Okay, so again, we're going to draw this. Okay, so now you're going to blend all four of these together. So that means the energy that should result, there's 3/4 of it are p orbitals and only 1/4 of it is an s. It should be 3/4 of the way up from s to p. It should be up there somewhere. So I'm going to go ahead and draw it kind of close to this orbital, but not all the way up there, of course. So that's going to be 2sp3. Now remember, again, don't let that number fool you. It's 4 orbitals. S, P, P, P. When you start with 4 orbitals, you end up with 4 orbitals. That's the way to think of it. Okay, and that's what that would look like. And that's typical of methane, which has a hydrogen here, a carbon in the middle, a hydrogen flat on the paper right there. These two are on the paper. Then we can have one coming out. This is the perspective model. So it's kind of that fat leg right there. That means it's coming out of the page toward you. And then the dashed line means it's going back into the page away from you. So it's like a 3-legged stool with a hydrogen up on top there, okay? And those are all equal bond angles, even though I didn't really draw it to make it look like that. Those are all 109 degrees. So they all have equal energy because they all have blended to form 4 equal energy bonds. All right? Okay, so question 3A. What is an extended octet, and which periods rows on the periodic table can have an extended octet? So I'm going to go ahead and write out that answer. Okay, so an extended octet can occur when the central atom has more than 8 electrons, and it's either going to be 10 or 12 in its valence orbital. And let me add this. Okay, so the extra electrons are held in the d orbital. Okay, draw a 3sp3d hybrid. Okay, let's find out where that is. So that's if you have 5 electron domains right here. And so here's the example. It would be trigonal pyramidal if all 5 are bonding to something. This one you only have 1 bonding, or 4 bonding and 1 lone pair. This one you have 3 bonding and 3 lone pair. But anyway, that's going to form an sp3d orbital. So let's go ahead and draw that. So we have, so now I have to make it a 3s, because there's no such thing as a 2s. And I didn't answer that question. Which rows can have an extended octet? So let me write that up here, okay? The ones is the 3rd row and below. Okay, so the 3rd row and below can have an extended octet. Why is that? That is because they have d orbitals. The 3rd row has a d orbital. There's the 3rd row. Remember that the 3d orbital, you just have to memorize this, is 1 row below its number. So it's in the 4th row. So this is the 3d orbital. That's the 4d orbital in the 5th row. That's the 5d orbital in the 6th row, and so on, okay? So it has to have a d orbital in order to have, it's like a storage locker for those extra electrons. It has to have a d orbital. The s and p can only hold 8 no matter what. So you have to have a place to put those extra electrons, and it would be in the d orbital. Okay, so let's go ahead and draw this. This is going to be a little tight here. I didn't leave a lot of space for this. And then I'm going to draw the d orbital. Now the 4s would come before the 3d, but we're dealing with the d orbital here, so I'm not going to bother to draw that. There should be a 4s before you get to 3d. And these funny labeling letters are xy, xz, yz, x squared minus y squared. No math involved. It's just a name that for some reason they gave it. And then 3z squared. Okay. So if I'm going to create a hybrid, I don't have space to do it over here. It's going to have 1 part this, 3 parts this, and 1 part this. So it's going to be somewhere pretty close to the P, actually. There's more space between this than there is between this. So I'm going to say, I don't know, I'm just going to draw it over here. But anyway, what you're going to have is 5 of them. You're going to have these forming. They're going to all blend together to be at the same energy level. I won't write the 3 part of it. I mean the third, 3 out in front there. It's in the 3rd orbital. It could be in any orbital though. In this case we said 3. And that's it. So all 5 of these, it's a blending of these. You're putting them all in the pitcher and mixing them together and shaking it up, and you come out with 5 orbitals that all have the same energy level. Okay, because when you look at this molecule, phosphorus pentafluoride, there's no reason why this phosphorus fluoride bond should be any stronger or higher energy than this one or than this one. They should all be the same. So you have to mix the orbitals in that fashion so that these 3 different energy levels you have here will all be at the same energy level. That's the whole point of hybridization. Okay, what is a hybrid orbital? All right, so what I did is I asked you to repeat these questions. Again, I want you to write it out. See if you can do it as much from memory as possible. And so it's not a mistake that I asked them twice. And go ahead and do that, okay? And that goes all the way down. Let's see where it goes. It goes all the way to the bottom of the page. Same questions. And all the way to 3B. Draw exactly what I just drew just a second ago. All right? Okay, so now let's keep going. I'm going to go down to number 4. Okay, 2 rules of thumb to determine if a molecule is polar. So let's just take water. It's the most common. Water versus carbon dioxide. So there's water, H2O. That's a polar molecule. Oxygen, that's an O for oxygen. Oxygen is more electronegative than hydrogen, so the electrons, these electrons tend to get pulled towards the oxygen. So the polarity, so we can draw a better arrow than that, the polarity is in the direction of the oxygen. The negative charge is in the direction of the oxygen. That's where the electrons are getting pulled. Carbon dioxide looks like this. Okay? And what you want to look at is lone pairs. There's no lone pairs on the carbon. There are lone pairs out here, but not on the carbon, and that's key. All right, so the 2 rules of thumb are, these are just rules of thumb, but they generally will be pretty accurate almost all the time. Is the molecule lopsided? Is it uneven? The second one is, and this is almost always true but not quite, does the central atom have lone pairs? So let's look at water. Okay, it's lopsided. If it were symmetrical, you'd have a hydrogen on this side and another on exactly the opposite side, just the way carbon dioxide is with oxygen. Okay, but you don't. It's lopsided. And it has lone pairs on the central atoms. What these are doing is they're taking the electrons. Remember, these are electrons right here and here. It's taking those and it's pushing them down that way. That's why water is a lopsided molecule, or the hydrogens are pushed down here. If there weren't any lone pairs here, water would be a straight molecule just like carbon dioxide. So does it have lone pairs on the central atom? Almost always. I would say 90-95% of the time. If it does, it's going to be a polar molecule. Okay. Now, which way is it polar? You just have to then ask yourself, which is the more electronegative? Is hydrogen more electronegative or is oxygen? And the answer is oxygen is more electronegative, so the electrons are going to be pulled in the direction of oxygen. So that's a separate question as to which way the polarity is. Okay, you look at carbon dioxide, and it's perfectly symmetrical. It's not lopsided. It's perfectly even, and it doesn't have any lone pairs on the central atom. That's why it's not pushing the oxygens in some odd direction like the water molecule is. Okay, so generally when you look at it, you can kind of tell just by using those 2 rules of thumb. Okay, what is a sigma bond? All right, so sigma bond. This is in the notes. I never brought this up in class. Again, everything really in this class has to be kind of learned from reading the notes or watching the videos. And I have not read the notes, so I'm counting on you to read them. I have not done a video of the notes. I may do that before the end of this weekend. So this is the weekend. Today I'm recording this on Saturday, January the 9th. All right. So a sigma bond. Okay. So it's a sigma bond is this bond right here and this one right here. It's directly between, and it's called the internuclear axis. That just means between the nuclei of the two atoms. Okay, so this one and this one, or this one and this one. In other words, most bonds, all single bonds, let me write that, all single bonds are sigma bonds. So it almost sounds like a poem. They're directly between the two atoms that they're bonding. And you're saying, well, what's the alternative to that? Oh, and I'll show you in a second. Okay, all single bonds are sigma bonds. So these are sigma bonds because it's directly between the oxygen and the hydrogen. Now, what is not a sigma bond? Well, then the next question is, what is a pi bond and what orbitals form pi bonds? Okay, pi bonds Okay, so pi bonds are formed by unhybridized p orbitals. Okay, so back here when we talked about the 2sp and it formed these two hybrid orbitals, and then we said these two p orbitals are unhybridized, and we said that's where they form double bonds or triple bonds. Okay, carbon dioxide just has enough electrons to form a double. Something else like HCN would form a triple bond. Or nitrogen, N2. Let me draw an N2 for you real quickly here. N2, which is a nitrogen, it's just the diatomic molecule, has an electron pair here and here, but it has a triple bond in between it. So that would be formed by, that actually I should have drawn that. No, that's right here. So one of these is the sigma bond. It's the two sps that are going in between. Okay, and the way to look at it is this nitrogen has two sps. There's one of them. I'm just going to say it's that bottom line, and there's the other one. An sp orbital hybrid does not have to be bonding. It can be a lone pair. So there's an sp, there's an sp. This one also has an sp there. That's what's bonding with these two together. And then it has an sp there. Now these two additional bonds are formed by the 2p y orbital of each atom joining hands, holding hands, and bonding together, and the 2p z orbital holding hands and bonding together. And the way those look is the 2py's would be sticking up and down like this, and the 2pz would be coming out of the page towards you and going back away from you. That's where those two extra p orbitals would be. So one of the three bonds is a sigma bond. It's directly, well, if you want, you can say it's the one in the middle. It's the one directly between these two. Doesn't matter which one you say it is. Okay, and then the other two bonds are called pi bonds, and that's what forms the double and triple bonds. And they're up here. So I'm going to actually draw you a better picture of this. So for nitrogen, it's going to look like this. Here's a nitrogen. And let me see if you have. I'm going to do this actually back here, okay? So what type of bond forms a double or triple bond? The answer to that is just write it simply pi bond. That's it. Okay? It's one of those unhybridized p orbitals. So let's go ahead and draw a picture of nitrogen here. Even though I didn't ask you to do it. It's going to look like this. And it's got these lone pair out here. And then it's got a bonding pair in here. So what it's going to look like is this. this is going to be an sp coming from this nitrogen. And again, it formed an sp because it knew that it was bonding with another nitrogen. So that's an sp. There they are. Now, what happened to the other sp here? Because when you have an sp, you have two of them. You don't just have one of them. It goes out the backside, and it belongs to that lone pair. That's what that lone pair belongs to. That's an sp. Same with this one. It has a lone pair over there, and that's an sp. So these, they're directly between the two nitrogens. That's a sigma bond. Actually, I want to write that. I don't want to write that there because I'm going to need that space. Okay? Somehow I'm going to write that this, let me write it way over here, is a sigma bond. And it is between the atoms, directly between them. Okay, so now what about that double and triple bond? It's going to be hard for me to draw perspective, guys. You're going to have to work with me on this. One of them, the first one for the double, the second of the three bonds, goes up here, and it looks like this. You look at it, and you can look at this online or in my notes, and this nitrogen is contributing an electron, and this nitrogen is contributing an electron, and they basically bond together. Now notice they're not directly between the nitrogen atoms; they're up above. Now this is called the pi bond, and we're going to call it pi y. So it's a p orbital and another p orbital, basically up above, and also below. Okay. Now, the electrons are somewhere. There's two electrons. They're either here, or one of them's here, one of them's here, but they're either above or below. So this is also pi y. Okay, if I try to draw pi z, the third of the triple bonds, it's just going to be a mess. So you just have to kind of listen to what I'm saying. It's exactly the same as this one, except it's coming out of the page, and it's going back into the page. Okay, again, if you look at the notes, or even look in the book, or look online for pi bonds, you can look up pi bonds on Google and go to images. You'll see some good images of that. So this one goes above and below, that with the y orbital, and the z comes out and goes back. So neither of these, the electrons you can see are kind of up above. They're not right between the atoms. So that's a pi bond, and that's what forms a double bond. And then the triple bond comes out and goes back in. Okay? So sigma bonds are any bonds. Any single bonds are sigma bonds, and they're directly between the two atoms. All right? And then there's the answer to that. Okay, I am going to wrap this video, get it up online, and now I'm going to do the book problems with you here. And again, you don't do every one that's listed on the front. I left that there for my reference, but I copied the ones that I want you to do. All right, so I'll see you on the next video.